Hi, today we are going to see about PN compensation. Proportional controller, that is P controller, with a unique example we are going to see. With this example, our readers' knowledge about stability and steady state error will also enhance. Consider the feedback control system as shown in figure. Characteristics equation of this control system can be written as s cube plus 3s square plus 2s plus k equal to 0. If the root Hurwitz is applied in this characteristic equation, then the range of k for the stability can be found as 0 to 6. It implies that for the values k greater than 6, the system will be unstable. For the value of k equal to 0, the system will be marginally stable. Root locus of the system shown in figure. Root locus provides an idea that what should be the value of k. You can understand that root locus is drawn from the open loop transfer function g of s h of s, but it gives an idea about the poles of the closed loop transfer function. In characteristic equation, the root locus is helpful in designing the value of k. So the system is stable for values such as k equal to 0.2, 1, 5.8, etc. But what value we should select? To analyze each value and show you the results. High value of k, for example k equal to 5.8, it will reduce the stability but improves the steady state performance. For the values of kp, kv, ka, the steady state error is given in this slide. It can be observed that for the high value of k, values of kp, kv and ka will be high and steady state error will be low. For k equal to 0.2, this case characteristic equation of this system is s cube plus 3s square plus 2s plus 0.2 equal to 0, and the roots of these equations are minus 2.088, minus 0.7909 and minus 0.1211. Ignore the value minus 2.088 as it is far away from imaginary axis. On the basis of the remaining two roots, it can be termed as an overdamped system. Against step input, its time response is shown in figure. It can be seen that the response has no oscillation. The over system has damped value. In the present case, open loop transfer function is g of s h of s equal to 0.2 divided by s into s plus 1 into s plus 2. Its gain margin is equal to 29.5 dB and phase margin is equal to 81.5 degrees. It should be noted that in the designing of control systems, overdamped systems are not preferred. Roots should have slight imaginary parts. In the case of overdamped, damping is more than 1, while damping around 0.8 is preferred. For k equal to 1, in this case, the characteristics equation of the system is s cube plus 3s square plus 2s plus 1 equal to 0, and the roots of these equations are minus 2.3247, minus 0.3376, plus or minus j 0.5623. We can ignore minus 2.3247. On the basis of the remaining two roots, it can be termed as an underdamped system. In the present case, open loop transfer function is given above as g of s h of s equal to 1 divided by s into s plus 1 into s plus 2. Its gain margin is 15.6 dB and the phase margin is 53.4 degrees. Response has oscillations. It is the response of an underdamped system. For the value of k equal to 5.8, that is, it is very close to 6, so you can understand that system is stable. You can find the characteristics equations and its roots. One root can be ignored, the remaining two roots will be very close to the imaginary axis. Against step input, Its time response is shown in this graph. In the present case, open loop transfer function is g of s h of s equal to 5.8 divided by s into s plus 1 into s plus 2, and its gain margin is equal to 0.294 dB and the phase margin is equal to 0.919 degree. It can be analyzed as compared to the previous cases. The gain margin and phase margin are reduced drastically. As the system is very close to instability, hence the gain margin and phase margin are also very close to zero value. Activity. Proportional and integral controller. As the name suggests, it is a combination of proportional and an integral controller. The output is equal to the summation of proportional and integral of the error signal. Now let us analyze proportional and integral controller mathematically. Output is directly proportional to the summation of proportional of error and the integration of the error signal, writing this as mathematically in the form of a of t directly proportional to integral 0 to t e power t dt plus a of t. Removing the sign of proportionality, a of t equal to k integral of 0 to t e of t dt plus kp e of t, where ki and kp proportional constant and integral constant respectively. Though the PI controllers, we are adding 1 poles at the origin and 1 0 somewhere away from the origin. As the pole is at the origin, its effect will be more, hence PI controller may reduce the stability. It reduces steady state error drastically. Due for this reason, it is one of the most widely used controllers. Example, the schematic diagram of the PI controller is shown in this figure. Against step input for the values of k equal to 5.8, k equal to 0.2, its time response is shown in figure 2. At k equal to 5.8, P controller, it was on the verge of instability, so just by adding the small values of an integral part, it became unstable. Note that integral part reduces the stability, which does not mean that system will be always unstable. In the present case, we have added an integral part and the system is stable. The response of the system shown in figure 2 with k equal to 5.8 and the constant integral constant ki equal to 0.2. Thank you.